This is the last video in the initial math review series, and the topic of this one is vector calculus in curvilinear coordinates, which is something that you should already know, and you should already have seen all the material that I'm about to present here. But just for completeness, and because it's important, I'm going to do a quick review. If this material is still somewhat shaky in your mind, I recommend that you peruse this book over here, called Div, Grad, Curl, and All That by Shea. It's quite a good book, and it goes over everything that I'm about to do here in considerably more detail. So let's begin by looking at the case of planar polar coordinates and what happens in that case when we are working with differential displacements. So let's say that we have a vector, position vector like this. I'm going to call it L, and to it we will add a small differential displacement, dl. Okay, so since we're working now in planar polar coordinates, the component vectors of this displacement vector dl should be onto the unit vectors of this particular point here. So then we have the phi hat direction like so, and the r hat direction like that. So the component vectors will therefore be the L sub phi in that direction, and the L sub r in the r hat direction. So from this follows that we can write the displacement vector dl as the sum of dlr and the vector dl phi, which is just the magnitude of dlr in the r hat direction plus the magnitude of dl phi in the phi hat direction. Okay. Now the displacement dl here, if you add it to L, it gives you a change in coordinates. We're starting out at some coordinate here, r and phi, and we're ending up over here at some other coordinates, r plus dr, phi plus d phi. Right? Now we can also indicate the phi in this manner here. This is going to be the phi, roughly speaking. So let's just write this out here. Now the magnitude of the components of dl here, dl phi and dlr, can be directly related to the changes in the components d phi and dr. For dr, that's pretty simple. We simply have that dlr is equal to dr. In the phi direction, that's kind of different, though. The L sub phi, that is the component of the L in the phi direction, is a distance. The phi is an angle. So there has to be some scale factor in between, and that's going to be the length of this vector here. The length of that vector is r. So we get that the L sub phi is r times d phi. R is known as the local scale factor, and it's usually indicated by the letter h. So in this case we have that h sub phi equals r, whereas h sub r equals 1. Those are the scale factors for the planar polar coordinates. So they tell us something about the local scale here in the planar polar coordinates. In fact, if we bring in the polar coordinates here with some coordinates lines shown, we can see here that this distance from there to there is different depending on the size of r, and that varies with the scale factor r here. So this distance here between coordinate lines, between crossings of coordinate lines, is proportional to this local scale. And this local scale determines how we do calculus with vectors, because calculus with vectors is going to depend on essentially doing things with these differential length elements dl. Okay. Now let's just do this a little bit more in general. So let's say that we have a vector L in some curvilinear coordinates, and we're not specifying what they are. So at this point we have some curvilinear coordinates that go through that point. There should be orthogonal curvilinear coordinates. So these are just coordinate lines in this particular coordinate system. We're adding in a differential vector like that. Actually, let's make it a little bit longer. Doesn't look very differential, but it makes it easier to see what we're doing. So we now have unit vectors. This becomes e1 hat. This is e2 hat. We can decompose the L onto those unit vector directions, like that. This is dl2, dl1. Okay. So just as before, dl corresponds to a change in the coordinates. We go from L, which depends on R1, R2, and R3. Goes to L, which depends on R1 plus the R1, etc. L at R1 plus the R1, R2 plus the R2, R3 plus the R3 equals the original L plus the L. This relationship suggests that you can rewrite the L as follows, using just a chain rule. This derivative here of this vector, dl, with respect to dr1, is going to be in the direction of e1 hat, because that's the direction in which dl changes if you change r1. So it's going to be along e1 hat, and the same thing for the other derivatives. dl can of course also be rewritten as the sum of its components along the unit vectors. And just as the case for the polar coordinates, we can rewrite this in terms of the local scale factors and differential changes in the coordinate variables. And making the identification between this third line here and the first line, we see immediately that hi is the absolute value of the derivative of the vector L with respect to r sub I. And that's the local scale factor. We can then show, I'm not going to do it, but it can be shown pretty easily, that for the curvilinear coordinate systems that we use the most, that's the cylindrical and the spherical coordinate systems, the local scale factors are the following. Cylindrical coordinates, the coordinate variables are rho, phi, and z, and the corresponding scale factors are 1, r, and 1. And then for the spherical coordinates, the coordinate variables are r, theta, and phi, with scale factors 1, r, and r times sine theta. So this is something you should have seen already. Keep this in mind now, but before we are actually using this, I'm going to rapidly introduce some of the vector operations that you need to be familiar with, and that I hope you already are quite familiar with. The first of these is the gradient of a scalar, the gradient of a function. So what the gradient does, it takes a scalar and it generates a vector. So we have a function f which depends on x, y, and z, let's say. So it's a scalar function. So we can plot it. I'm going to do this just in 2 dimensions here. So here is our coordinate system. So this corresponds now to f equals different constants. These lines, these are the constant contour lines, etc. This is the top here. So f is equal to c1 on this line, f equals c2 on that line, and c3 on that line. The gradient, as you know, is a generalization of the vector to a multivariable function. And it's defined in the following way. The gradient of f in Cartesian coordinates is the f dx, f dy, and partial df dz as a vector. Because of that, we can write it like this. This symbol here is the del, or the nabla symbol. And you can see that, if you like, as a vector that consists of the operations partial d dx, partial d dy, and partial d dz. So what we have here now is a vector that's been generated from a scalar function. And we can put this vector in here. The vector is going to point in the direction of the ascent, or the steepest ascent of the function, right? Which means that it will be perpendicular to the coordinate lines, like that. So that's one property that they have. The gradient vectors point in the direction of steepest increase in f. And also the magnitude is going to be proportional to the slope. So I didn't really draw that here, but the magnitude of the vector of the gradient vectors here is going to be greater than the magnitude over here, because the function f increases more rapidly. And as I just said, the gradient is perpendicular to the contour lines. That makes sense, right? The contour lines correspond to lines where there is no change in the value at all. If you want to have the most rapid change possible, you want to move perpendicular to those lines. And the final property follows from this is that if you have that the gradient of some function equals 0, well, that corresponds to a 0 slope, which means that you might be at a maximum or a minimum. So that's a gradient. That's probably the most useful of the differential operations we're going to perform on vectors, but the other ones are important too. And the next one is the divergence of a vector field. As you should know, this is an operation that takes a vector and turns it into a scalar. So we have a vector field, it's called F. The divergence of F can be seen geometrically as the flow out of a neighborhood of some point. So the divergence of F at the point R, it's the flow out of the neighborhood of R. So we can illustrate it like this. Here is a vector field, very particular one. You can see that all the vectors flow out from a point in the center here. So if you want to figure out how much is flowing out of this, the neighborhood of the center point here, what we will do is we'll define a curve around that point, and then we'll just integrate all along this curve, or all along the surface of this volume, the amount of flow out of this volume, and then we'll just shrink it down and make it smaller and smaller until it becomes infinitesimally close to this point here that we're interested in. So the definition then is that the divergence of F at the point R equals the limit as some volume shrinks to a small neighborhood around the point R of 1 divided by the volume V, and then you take the integral around the surface of V, that's what this around dV means, that's the surface of V, of F scalar n hat ds. So n hat is the normal vector to the surface surface of the volume that we are interested in. So if we take the scalar product that finds the component of F that points out of the volume and excludes the component that is parallel to the surface of the volume, which doesn't correspond to any flow. Okay. In Cartesian coordinates, the divergence of F is just the sum of the F sub x dx as a partial derivative, dfy dy, and dfz dz. This, if you like, can be seen as a scalar product between d dx, the vector d dx, d dy, d dz, and the vector f. So we can write this then as nabla scalar f. That's the divergence of that. And like I said, this is a scalar. So what we have here is a function that takes a vector, f, and turns it into a scalar. All right. The next important thing is the curl of a vector field f, and it takes a vector, the vector f, and it generates a vector. Okay, so the gradient goes from a scalar to a vector, the divergence goes from a vector to a scalar, but the curl of f goes from a vector to another vector. The best way to look at a curl, I think, intuitively, is to see it in terms of the effect that it has on, that a vector field has on a small sphere. Again, interpreting the vector field as a flow of some fluid. If we take a small sphere and place it somewhere in this fluid, and then assume this is a rough sphere, and then we'll look at whether or not it rotates where it is located. So this sphere here, for instance, will rotate because the flow on this side is greater than the flow on that side. So this sphere will rotate clockwise in this position. So more specifically, in 3 dimensions, the curl can can be seen as the microscopic rotation locally in the vector field, and the axis of rotation of the sphere that you have in this vector field is in the direction of the curl. So mathematically then, we define the curl of f, or its component in the n hat direction more specifically, as the limit of when an area goes, we take an area around a point r and reduce it to become small. It's in the limit of 1 over a times the integral around these circumference of this area of the vector field scalar dr. So that here is now my area. This is a. This is n hat. It's perpendicular to a. And the vector dr is along the edge here that makes up the boundary of a. If we take the vector field and calculate this here, then we get the circulation of the vector field here that corresponds to rotation along this axis. Now we have to calculate this 3 times then in order to get the full curl, right? Because this only gives the rotation along this axis. We'll also do the same thing for some other area that's perpendicular to this axis. It's going to be like this, and then another area like so. So we get 3 components of the curl that then tell us what the effect is on a sphere that will be placed on this point if we interpret the vector field here as a flow of some fluid. So in Cartesian coordinates, we have that the curl of some vector field f can be seen now as d dx, d dy, d dz cross the vector fx, fy, and fz. It's supposed to be a y there. So we can see this as a determinant of the following: x hat, y hat, and z hat. d dx, d dy, d dz on the second row, and f sub x, f sub y, and f sub z on the third row. Okay, so that's the curl. The final thing that you need to know about, which you almost certainly already know about, is the Laplacian. The Laplacian actually takes a scalar and turns it into a scalar. So you may wonder what it has to do with vector fields, but it turns out that the Laplacian, which we write like this, of some function f, x, y, and z, can actually be seen as the divergence of the gradients of f. Sometimes it's just written as del squared of f. So it means that in Cartesian coordinates, the Laplacian of f is just d to f dx squared plus d to f dy squared plus d to f dz squared. All right, so those are the 4 important differential operations having to do with vector fields that you need to know about. I've given you the expressions in Cartesian coordinates. If we are working in curvilinear coordinates, things get a little more complicated, generally because we have these local scale factors to deal with. And remember that the differential element, the L, is h1, the r1, e1 hat, plus h2, the r2, e2 hat, plus h3, the r3, e3 hat. So these scale factors here will enter into all of the calculations of the gradient, the divergence, the curl, and the Laplacian, and you get some fairly complicated equations, which I show you here. So as you can see, here we have the Cartesian expressions for the gradient and divergence, and cylindrical and spherical coordinates, they get to be more complicated. Basically, you can find both of these by using these expressions here, which are valid for any orthogonal coordinate system. And here you have the same expressions, the corresponding expressions for the curl and the Laplacian. These expressions are in the back of the textbook, not the general one, but you're probably not going to be needing it. But these can be useful in some occasions when you need to calculate the curl or the gradient or the divergence in curvilinear coordinates. You don't have to memorize any of these, but you should understand how they come about. So this was a very rapid review of vector calculus in curvilinear coordinates. If this was too rapid, if there was something you didn't quite get, remember this is meant to be a review. So you're welcome to ask any questions you like in class, or else consult the div, grad, curl, and all that book that I recommended in the beginning of the video.